Welcome back. In this video we're going to look at how the gradient makes the calculation of the directional derivative so much easier. So if you recall from previous class, we defined the directional derivative through the use of a limit and a unit vector in the direction that you want to calculate the derivative, hence the name the directional derivative. But the limit definition can be quite bulky and time-consuming to use to actually calculate a directional derivative. What we find out now is that the gradient gives us a very quick and efficient way of finding the directional derivative. So the definition you see on the screen in front of you right now is for a function of two variables, and you have a particular point x0, y0 in the domain of f, where we know that f is differentiable. Then for every unit vector in R2, the directional derivative of f at the point x0, y0 in the direction of the unit vector u is equal to, here we have the gradient evaluated at the point x0, y0, that vector dotted with the vector u. So instead of using a limit calculation to find the directional derivative, we simply have to calculate the value of the gradient at the particular point and then dot that resultant gradient vector with the given unit vector. It's a dot product instead of a limit. Similarly, we have the three-dimensional version of finding the directional derivative. Nothing different there other than expanding the extra variable. So let's try this on a problem we've worked in class recently. Consider the function f of xy equals x squared plus y squared. Find the directional derivative of f at the point 1, 2 in the direction of u equal to 5/13, comma 12/13. So we could impose the limit definition, but I want to do it with the gradient instead. So first step being to find the gradient of f, which is very straightforward in this case. Remember, the gradient is a vector in this case with two components, where the first component is the partial derivative of f with respect to x, and the second component is the partial derivative of f with respect to y. So the partial derivative of this with respect to x is simply 2x, and the partial derivative with respect to y is 2y. So very straightforward calculation. Then we need to evaluate the gradient not in general, not at xy, but at the point 1, 2. So plugging in 1, 2, we get that the value of the gradient there is equal to 2, 4. Then to find the directional derivative in the direction of this unit vector u, we simply dot the vector 2, 4 with the vector 5/13, 12/13. 2, 4 dotted with 5/13, 12/13, which equals 58/13, which, if you recall from class the other day, is the same value we found when we used the limit definition. But this is much more efficient in finding that directional derivative. So, continuing on, what else does the gradient tell us? The gradient of f at a particular point p will always point in the direction in which f increases most rapidly. So it will point in the direction of most rapid increase, which this is very apropos to when we were talking about contour maps in class. How do you find which way is the steepest, or where could you find the direction that's not so steep? We can use the gradient to help us do that. So in different places here, the gradient vector has been drawn on this level curves of the three-dimensional surface. So at this point, the gradient would point in this direction, here it would point here, here it would point here, and so forth. Remember, with level curves or contour maps, that where the curves are more closely together is where the three-dimensional surface is more steep. And so here's kind of the more mathematical definition of that. We have a function of two variables. We got the point in the domain. If C is the level curve containing the point, then the gradient of f at that particular point and the level curve C are orthogonal. And again, if we look back at that picture, we can see that it appears to be that way, but this theorem guarantees that it will always be that way. The gradient will be orthogonal to the level curve, or normal, or perpendicular, whichever word you prefer to use. So let's see if we can find some problems, or solve some problems dealing with this aspect of the gradient. We're going to look at the function f of xy equals the arctangent of y over x at the point 1 square root of 3. We want to find three things: the direction in which f increases most rapidly away from that point, and then find the rate of change of f in the direction of that most rapid increase, and then also find the direction in which f decreases most rapidly away from the point 1 square root of 3. So we'll tackle them one at a time. Finding the direction in which it increases most rapidly is finding the gradient function and plugging in the particular point there. So the gradient function, you got to dig through your rules of derivatives. How do you take the arctangent of u, the derivative of arctangent of u? It's 1 over 1 plus u squared times the derivative of u. So finding the gradient here, when we take the partial derivative of f with respect to x, it's 1 over 1 plus y over x squared times the derivative of y over x with respect to x, which is negative y over x squared. And then likewise, for the partial derivative of f with respect to y, it's 1 over 1 plus y over x squared times the derivative of y over x with respect to y, which is 1 over x. If we simplify this through algebraic manipulation, it will simplify down to this very nice expression. It's just the vector negative y over x over the expression x squared plus y squared. We must then find the value of the gradient at the point 1 square root of 3 by plugging in those for x and y, and we get 1/4 times the vector negative square root of 3, 1. So this vector points in the direction of most rapid increase. The second question was find the rate of change of f in the direction of most rapid increase. The rate of change in f is simply the magnitude of the gradient function. So we've already found the gradient function to be 1/4 times the vector negative square root of 3, 1. So we just find the magnitude of this. We get 1/4 times 2, which is 1/2. So the rate of change is 1/2. And the last question was find the direction in which f decreases most rapidly from 1 square root of 3. Well, since we've already found the direction of maximum increase, we can find the direction of maximum decrease by simply going in the opposite direction. So it's the negative of the gradient at that point. So negative gradient evaluated at 1 square root of 3. This was the gradient at 1 square root of 3. We're just tossing a negative sign out in front of it. If you wanted to distribute the negative through, it would look like this instead. And so those are a few quick applications of the gradient. In the next videos, we'll be looking at extreme values and how we can use the gradient to calculate extreme values. But that's all for now.